Hello, I'm Lily. That's easier to pronounce. And today we're going to show a little bit of a different presentation that is about the wave community. So we're going to bridge the gap between testing and stuff that people that develop wave energy converters are interested in, and people that develop the reanalysis are doing. So we want to make some guidelines for users that are interested in developing or testing wave energy converters. I want to acknowledge my co-authors, Dimitra Denaxa and Gerasimus Kores from HCMR. So why we chose this topic? Because indeed wave energy started from here. It started from Japan, and it started as a means to power navigation buoys. And now we're not there yet, so there were a lot of failures with large-scale wave energy converters, and now it seems that we're going back to these little small-scale converters that are buoy-shaped. Of course, you can see also some other examples like in Sakata, Japan, that looks like a wave breaker. But indeed, it seems that the way forward is to use low power devices and to use them together with wind and solar. So why we need validation guidelines? We can, of course, get the product, compare it with satellite for significant wave height, or compare it with the buoys and get like a summary metric, but that will not be enough because there are a lot of things to consider. These are some examples of case studies we do. So one is the spatial resolution of the mean wave energy flux, and the other one is the average number of weather windows. So we need to have an idea of how many hours we can get continuous where the significant wave height remains below a certain value. Now, if we don't get this right in the range, then we cannot send the boat, or we can, but it will not be successful. There are some IC standards, but they are from 2015, and we want to see how we can revise them, because reanalysis have changed, so also the standards should change. So this is our reanalysis from HCMR. It's part of the MED-MFC. I'm not going to go into detail because there was a poster by Ali Aydogdu the other day with all three components of the Mediterranean Forecasting Center. And here we can see that we have two domains. We are interested in the small domain, the finer resolution. The other one is mostly to provide this boundary conditions, and it also ensures that we get the swell in the in our domain. So this is what we do by comparison. We get the model, we have a spectrum that we integrate over the directions, and then we integrate that spectrum over the frequencies, and we can get significant wave height, which is like a key value for us, and various periods. We're mostly interested in the energy period, but what the buoys usually provide is the second moment period, which is a bit more sensitive on the tail. And this is the one we're going to use because it's quality controlled as a proxy. And you can find the data, they are online, and yeah, they are quality controlled, as I said. So we use the deep water approximation for the wave energy flux. So that's the wave energy over the crest length, a bit different from what we do with wind or solar, that is over an area. And what we need is the square of the significant wave height and one period. It could be peak period, energy period ideally, but here we're going to use the mean period. And this is like a first validation. We get some offshore buoys located in the west part of the basin, and we get like a sum of the collocations between buoys and model. And we can see that the closer we are to the reference line, the orange one, the better the model is. It's not bad at all, actually. That's quite a good performance. Here we use it as a case study. We don't necessarily need to fix it, but we use it in our process. Of course, we can get all the summary metrics, as I said, like bias, like RMS difference, like scatter index, Pearson correlation, but we also need some qualitative approaches, and that's what we get here, the scatter plots. We also have quantile plots, so we can, in our opinion, we should also look at the extreme waves. So usually the 95 percentile is used as a threshold when we do peak over threshold analysis. So we need to know how the model is doing there. And here what we can see is that the model does very well during the operational range, that the wave energy converter can function. But we do get some overestimation for very large waves. So when we measure the forces for very large waves, we're likely going to overdo it. Now, by means of variability, that's another important thing that we need to know. So if there's very high variability, perhaps we should exclude that location. And it seems that the model here, we use like a very standard metric for the coefficient of variation. And that's like a ratio between the standard deviation and the mean. So if this is very high, we're just not going to select that area. So we talked about significant wave height, and then we have the mean period. So what we see on the top left panel is the response amplitude operator. So this is how a buoy will behave. What does it mean? A buoy that we want to use, whatever means to extract the energy. The one we prefer and the one that seems to be a winner is the oscillating water column, if you heard about it. If not, you will Google it. There are many nice animations online. And what ideally we want to have is quite a range of periods where a device can operate. So if this is like a very narrow range and we do not get the period right from the reanalysis, then we're going to have a problem because we're going to be out of resonance. It's like when you design a boat and you don't want it to be in resonance with the waves. Here it's the opposite thing. We want it to be in resonance with the waves. And that's what we try to see now with the period. The one thing we see again is the scatter plot. We see that in the entire range, we have an underestimation. So ideally, we should adjust it. And then we also see that for very, very long periods, that's more important for the moorings, we get an overestimation of the period. That's the extreme ones. And we also see the distributions here through box and whisker plots. So this is like from the 25 to the 75 percentile. And we do not see a very good agreement in the range of the quartiles in the interquartile range. So how we're going to fix that? We're going to try some bias correction techniques. There is very limited information in the literature about that for MED. Actually, there are like I've seen like 3 papers on that. And here we've tried 2 different methods. One is very simple for these offshore buoys. It's the delta change. So we get the difference between the means, the mean of observations and the mean of the model, meaning the observations are our ground truth. And then we adjust it. That's a bit naive in the sense that we say we have the same difference in the entire range. And then we have a bit of a more sophisticated method that I've heard a lot about being in the conference. And this is the empirical quantile mapping. So we work with the inverse cumulative distribution functions, and they're quite effective in aligning the ones of the model with the ones of the observations. And these are the 2. So what we see here as an example, as a result, is in the box and whisker plots are the observations. Then we have the model, that we have also the 95 percentile. These are the triangles, the pink triangles. And sometimes we get an underestimation, like for the model. For this very, very high, the tail of the distribution, we will get an underestimation. While for the 95th percentile, we did get overestimation. And we wanted to fix that. So by using the delta chains, it doesn't seem to work very well. This arrow that looks down, it means that it's not doing very well. And then when it smiles, it means it's doing well. So with the empirical quantile mapping, it's quite effective in going there and really adjusting the distribution. That's for the significant wave height. For the period, we have a bit of a more complicated situation. So what we do here, again, we can see that assuming a constant change, a constant difference in the entire range doesn't work well. So again, the empirical quantile mapping, it's quite effective. They look actually identical if you look at the observations and then you look at the corrected data set. So that's the one thing. As you remember earlier, we talked about an approximation, a deep water approximation that we can get for the wave energy flux. And there we need significant wave height and periods. So as you have in the wind turbines, you have like a power curve, and you know what this turbine is going to do, where is the cut-in speed, the cut-off, and so on. For waves, we have something similar. They're going to generate a power matrix that will show what is the power for each pair of significant wave height and period. So we want to be able to capture this very accurately, and that's the joint probability distribution of these two. This is what we see on the far right. And on top, we see, of course, that's the good result. I didn't include the delta chains one. But what we see that with the empirical quantile mapping, we get identical joint distributions. And that's not only important for waves, that's important for anything you're going to go and deploy in the sea. So I'm not going to go into details on that. It's in a paper. I can send it to you if you want. It's simplified here, some guidelines about how to proceed with this type of data, the collocations, and then we do the diagnostics and the variability analysis. But if our data are very much impacted by the tail, then we shouldn't be using the mean. And if you see like 90% of the papers, includes the mean when it comes to the wave energy flux estimation. So ideally, what we think is that the 50th percentile should be used, and then if necessary, to also perform a bias correction like we did here. We collected like buoys in the offshore that have similar characteristics. And I'll let you look at the concluding points. We've said them already. And we want you can contact us either on my email, sorry, that's a generation thing, or on the Poseidon website. And you can scan also the QR, that's for the Reanalysis, the Mediterranean Reanalysis. Thank you.